So in this video, I want to talk about the relationship between antiderivative and motion, specifically position, velocity, and acceleration. We've already talked about those concepts when we were talking about derivative. So you'll recall that if we have a function which means position as a function of time, so t is our independent variable here, and we take the derivative with respect to time, the rate of change of position, remember derivative gives us rate of change of position is called velocity. And if we take the derivative with respect to time again, we have the rate of change of velocity, the derivative of velocity, which is the second derivative of position, and the rate of change of velocity we call acceleration. Well, I assume that looking at this, the role of antiderivative is starting to become clear. If we start off with acceleration and we take the antiderivative with respect to time, we get back to velocity. And if we take velocity and we take the antiderivative with respect to time, we get back to position. So position, take the derivative with respect to time, you end up with velocity. Velocity, take the derivative with respect to time, you end up with acceleration. And antiderivative takes us back from acceleration to velocity and from velocity to position. Let's take a look at a problem. The ball is thrown upwards from a height of 2 meters with an initial velocity of, let's say, 30 meters per second. A little bit more than 60 miles per hour. That's pretty fast, especially to throw a ball directly upwards. Not a natural throwing position. So in part A, let's just go ahead. Oh, haven't given you the remainder of the problem yet. So the acceleration due to gravity is 9.8 meters per second. Oh, sorry, meters per second per second. 9.8 meters per second squared. 9.8 meters per second every second. So part A, let's write a formula for velocity. For acceleration. Let's start with acceleration. Now, I've told you over and over again to define your variables. The one kinds of variables I'm not going to make a big deal of are velocity and acceleration. So if you want to call acceleration A in a problem where you're dealing with velocity and acceleration, I'm okay with that. I will know that A means acceleration. But if it helps, I'll just write A equals acceleration. So A of t, A is a function of t, 9.8 meters per second is the acceleration, but acceleration due to gravity is downwards. Things accelerate downwards. So it's actually just a constant minus 9.8, and the units would be meters per second squared. A of t equals a constant 9.8 meters per second squared downwards. So I basically just told you that in the problem. So B, let's write a formula for velocity. So a formula for velocity. We know to go from acceleration to velocity, we want to go ahead and take the antiderivative. So velocity is going to be the antiderivative of acceleration. You know from your rules for antiderivative, what the antiderivative of a constant is. Last time we were using x as our independent variable. This time, as I said, we're using t as our independent variable. So what's the antiderivative of minus 9.8? Well, it's minus 9.8, so v of t is going to be minus 9.8 t. If our independent variable was x, it would be minus 9.8 x. You can look back at your antiderivative rules from last time, and you'll see that you have a rule for taking the derivative of a constant. And that's all there is to it. So now, if you have a particular time, 1 second, 2 seconds, 3 seconds, you can go ahead and plug this in, and you'll notice that I've left something out when I wrote this down, because I wrote minus 9.8 t, but I left something out. Plus a constant. Minus 9.8 t plus a constant. So we don't end up with constants when we're taking derivatives, but we do end up with constants when we're taking antiderivatives. And now, in this example, I want to show you what those things mean. How can we figure out what this constant is? We're told in the problem that our velocity at time 0 is equal to 30. But according to our formula, that's equal to minus 9.8 times 0 plus c. So 30 is equal to 0 plus c. So c in this case equals 30. So my actual formula is equal to minus 9.8 t plus 30. In other words, when you take the antiderivative, when you go from acceleration to velocity, you can't figure out how fast you're going at any particular time until you know how fast you were going at somewhere. In this case, I told you how fast you were going at time 0, the initial velocity, the time where we let go of the ball. I could have just as easily told you how fast the ball was going after 3 seconds, and you could have plugged in 3 here, and you know, if I gave you the speed after 3, the velocity after 3, you could plug it in here, and you could have worked out c the same way. So when you go from acceleration back to velocity, you need to know how fast you were going at some time to be able to figure out what your constant is. And this is why the constants appear when you're doing antiderivative. So let's do one more. Find a formula for the height. And I'll define h, write my problem here, at time t. So you don't have to define h because I did it right in the problem. And we'll make this in meters. Well, we know to go from velocity back to position, we take the antiderivative. So you have a formula for velocity. To go back to position, in this case height, we take the antiderivative. So minus 9.8. The antiderivative of t is going to be 1/2 t squared using the antiderivative power rule, plus the antiderivative of 30 is going to be 30 times t. Again, if we were using x as our independent variable, it'd be 30x. Right? Plus the constant. And we can simplify this a little bit. Minus 9.8 times 1/2 is minus 4.9 t squared plus 30 times t plus the constant. And again, we'd like to know what the constant is. So let's go back to the original problem and look for some information. We know that at time 0, we're at height 2 meters. So h of 0 is equal to minus 9.8 times, minus 4.9 times 0 squared plus 30 times 0 plus c, and it's supposed to be 2 meters. So c equals 2. So we can go ahead and write our final answer. H of t is equal to minus 4.9 t squared plus 30 t plus 2. And again, if I tell you how fast you're going and I ask you where are you after 5 seconds, you don't know where unless I tell you where you started or where you were after 1 second. I have to tell you where you were at some particular time for you to work out where you are. If I say I'm in an elevator and I'm going up 4 floors per minute, where am I after 2 minutes? Well, you don't know unless I tell you what floor you got on. I have to tell you where you are at some particular time. You do know if you're going up a floor 4 a minute, after 2 minutes, you're 8 floors higher than you were when you started. That's a slow elevator. But you have to know where you are at some point to figure out where you are at all other times. So position, take the derivative, takes us to velocity. Derivative again takes us to acceleration. Antiderivative takes us backwards. And here we have an example.